So we already have some familiarity with acids and bases and some reactions of those. What we want to do here is take a look at acids and bases in more depth. So we'll start with some of the properties of these. The At the particle level, we typically think of acids as things that have hydrogen ion and bases as things that have hydroxide ion. And so we'll go into a little bit more depth about what that means. Back before we knew um, the dangers of chemicals, um, chemists would identify acids and bases based on their taste. So they would actually put some of them in their mouth when they were doing synthesis reactions to identify whether it was an acid or a base. And acids tend to taste sour, where bases taste bitter. So it's very easy to differentiate between the two. You can think of a lemon, which has citric acid and ascorbic acid, which is vitamin C, as having that sour taste. And bitter would be something like baking chocolate or soap is bitter. So those tend to be bases. Acids and bases are both very corrosive if they're concentrated enough. So acids tend to be corrosive to metals, and bases tend to be more corrosive to tissue. So like living tissue, skin, and hair, and that kind of things. When we look at um, their reaction, the ability to neutralize things. Again, we may have already studied this, but acids tend to neutralize bases, and bases will neutralize acids. We'll want to identify, not by taste, but we'll want to identify whether something's acid or base, and so we'll start to use some indicators. Two of the common ones that are used are phenolphthalein and litmus paper. In base, phenolphthalein is going to appear pink, and in acid it is colorless. Litmus paper in base will be blue, so it's easy to remember, base and blue, and in acid it will appear red. Right? So these are some of the basic properties of acids and bases. Now we're going to take a look at some definitions of acids and bases. So the first definition that we have is the Arrhenius definition. So this is the most fundamental, basic level, kind of like our flat Earth theory. It works for some situations, but not all of them. So an acid is going to be something that, when dissolved in water, increases the concentration of hydrogen. So these tend to have the H listed in front. So we have our kind of common HCl, HNO3, so hydrochloric acid, nitric acid, and perhaps acetic acid, HC2H3O2, right, which is in vinegar. Bases, when dissolved in water, increase the concentration of hydroxide ion. So this would be our ionic substances that have hydroxide as the anion. So NaOH and KOH are good examples of these. Remember, the alkali metals are going to dissolve and ionize 100% in water. So they would give those OH minus ions up. And again, the acids tend to give up the hydrogen ion. So those are our kind of basic fundamental level definitions of acids and bases. Now, going to a more advanced or deeper definition, we have what's called the Bronsted-Lowry definition. Here, the acid is going to act as a proton donor. So we can still look at obviously the hydrochloric acid has to be included in this definition as well. So if we look at HCl, we can think of that as donating a hydrogen ion and then having left behind a chloride ion. Or if you looked at an acid like cyanic acid, so HCN, again, it would donate a proton, and then you're left with the Cn minus ion. Now, a base is going to be a proton acceptor. So this doesn't have to necessarily be the hydroxide ion, although it could be. So this is going to open up our repertoire of what can be bases. If we look at the hydroxide ion, we have an OH, and I'm just going to add the dot structure in here. And so that ion has a minus charge to it. Accepting the proton, so here's my proton, remember that has no electrons, and so this pair of electrons on the base is going to donate to make the bond between the OH and the H, and in this case it's going to make water. And so that makes the hydroxide, the base here. If I use the other ion, the Cn minus ion, so we've got C triple bonded to N with a pair of electrons on that there. So again, we have the hydrogen ion. It can be donated. The hydrogen ion will get donated to the cyanide ion, and we'll make HCN, right, which makes that cyanide a base because it's accepting a proton. The proton's being added onto it. So these are the two basic definitions that we'll be using. There are more advanced ones, but we'll just start with these. Now, using the Bronsted-Lowry definition, a substance can actually act as both an acid and a base. For instance, the bicarbonate ion, so HC2, HCO3 minus. So we can see that this ion can donate a proton to yield the carbonate ion, or it could accept a proton. Right? So this is kind of an interesting property. So that makes this amphoteric, meaning that it can both act as an acid and a base by donating a proton or accepting a proton. If we look at this on the particle level and combine the acid and the base, so in this case, the hydrogen from the HCl is going to be the proton that's donated, and water is going to act as the base here. So that proton is going to go to the water, right? So the HCl is donating the proton, the water is accepting the proton, and you end up with H3O plus and Cl minus. Now, the other relationship we need to do with the Bronsted-Lowry is realize how these species are related together. So if we look at this, the HCl is going to be an acid. It's acting as the acid here. When it loses the proton, it then becomes a base. And so the two of these are related. The HCl and the Cl minus are related as acid-base conjugate pairs. And if we look at the water that we started with, this was acting as a base here, and it becomes the hydronium ion, which we'll learn more about the name of that, but the H3O plus, and the H3O plus then is going to be an acid. And so that's an acid-base conjugate pair. So we create these pairs when we're working with the Bronsted-Lowry definitions. Now we'll look at kind of an example of that here. We have nitrous acid reacting with water to produce conjugate base, the nitrite ion, and the conjugate acid, the hydronium ion, the H3O plus. And so you can see how this is related. So any acid-base reaction, you'd be able to come up with these pairs with the acid conjugate base and the base and the conjugate acid. So we'll do some practice problems like these in class. All right, our final topic for this introduction is to take a look at the acid-base strength, or the strength of acids and bases. And for our introductory level here, what we need to remember, primarily is that we have some strong acids, which are at the top of this list over here, and all the other acids below that are considered weak acids. So as you go down here, these are all going to be weak acids. Now, what does it mean to be strong and weak? Well, if I take HCl and I put that in water, right, that is 100% going to form the H3O plus the Cl minus. You won't have any of the HCl's left in solution. So that happens 100%. If we take one of the other acids down there, for instance, the HF, if I combine this with water, here we'll still get the hydronium ion, the HCl plus, so it'll still donate the proton there and the fluoride ion. However, in this case, instead of going 100%, this goes very little. So this maybe goes, probably less than 1% of those HF molecules will break apart and protonate the water to go this way. So in actuality, most of it stays as HF molecules. And so we want to think about what that looks like on the particle level. And we'll go over some examples of that in class. So that's kind of the end of our introduction to acids and bases. Make sure that if you have any questions that you read things over in your book and that you come in and see the instructor for help if you need it.